Okay, I'm going to continue with where we were before, working this problem here with two end-to-end spring elements. They have the same K, 1,000 newtons per meter, and we got to the point where we had formulated our global stiffness matrix from our element matrices, and we had an unknown displacement, and we used one of the equations, the second equation that's contained in this matrix formulation, to solve for x2, and it turned out to be half the or the average of the two end displacements. It was positive. All of this was delivered by the methodology of 0.1, so that doesn't enter into the picture. And our units, newtons per meter. This is meters, so this will deliver newtons here, and the same will happen here. So what we're going to wind up with is newtons. So if we calculate that, F1 is equal to 200 newtons minus 150. It's going to be equal to 50 newtons, and it's positive, so that means that it's to the right, okay? Which it should be, because our initial conditions were that, not initial conditions, our boundary conditions were that x1 is 0.2 and x3 is 0.1, and therefore this whole system is going to be in compression, and that means that F1 actually will be to the right. Now when we solve for F3, it should be to the left, so it should be negative. So let's do that, and we use a third equation for that. F3 is equal to, all right, 0 multiplies the 0.2. We have negative 1,000 times x2, which is 0.15, and then plus, it's 1,000 times 0.1 plus 100, okay? Because 1,000 times 0.1 is 100. This is newtons per meter, this is meters, so this is going to be newtons. This is newtons per meter, and this is going to be meters. Those cancel out. So what we wind up with, F3, is equal to minus 150 plus 100. These are both newtons. So it's equal to minus 50 newtons. Okay? Or equals 50 newtons to the left because of the minus sign there. So if we go back and look at our problem with these results, yeah, that works. Obviously, this is a static problem, so F3 has to be equal and opposite to F1, and our methodology delivered exactly that. Our nodal displacement is half, it's the average of these two, and it's to the right because both of these are to the right. Okay? And then the other thing that we can get, since we now know the nodal displacement here, is we can go back to the element matrices and actually find out what the internal forces are at x, or at node 2. So let's do that. We know that x1 is equal to 0.2 meters. x2 is equal to 0.15 meters, and x3 is equal to 0.1 meters. Okay? Now, if we look at our element 1, so I'll put a 1 with a little square in it to indicate we're talking about element 1, we do have F1 and we do have F2. Okay? We've solved actually for F1. Well, actually, we have we don't need that. This is 1,000. This is minus 1,000. Let's just keep going and see where this leads. 1,000 and then we know that x1 is 0.2, and we know that x2 is 0.15. Okay? Now we know what F1 is. You can actually see that from here. We'll just work that out with that equation. This is going to be 200, and that'll be newtons, and this will be minus 150. So this is going to be 50 newtons to the right. Okay? Now F2 is going to be the force on the node of spring 1, so it's going to be minus 200 plus 150, and so this is going to be minus 50 newtons, or 50 newtons to the left. Okay? So our first element looks like this. 50 newtons minus 50 newtons. Or actually what I should do, I'm going to leave the minus off because that can be ambiguous. 50 newtons, but it's pointing to the left. Okay? And so what we see when we look at this, when you compare it to the original overall problem, with the overall problem, we have 50 newtons this way and then 50 newtons this way, and now what we've seen is we've seen that on this element here, element 1, we actually have a 50 Newton force acting to the left. And then if you look at element 2, so we'll do exactly the same thing that we did with element 1. This is going to be F2 and F3. And we know it's not minus, it's a plus. So this is 1,000 minus 1,000 minus 1,000, 1,000. And we know our nodal displacements now. We got them from solving the global problem. So x2 is 0.15 and x3 is 0.1. So if we look at this, we'll find out that F2, let's keep it in the matrix format. F2, F3 equals, and then this is going to be a vector over here because it's a 2 by 2 by a 2 by 1. So this is going to be 150 minus 100. Okay, and then this will be minus 150. 150, sorry. Put that in there correctly. And this is 100 plus 100. So what we get from this is we get that F2 is positive. It is 50. And F3 is, we've already figured it out because we figured it out for the global, from the global matrix, but as you can see, we're going to get negative 50. These are newtons, and so if we look at our second spring, this is node 2, put a circle around it, and this is node 3. So what we've just discovered is that F2 acts to the right, and this is 50 newtons because it's positive, and F3 acts to the left, it's negative, and it's also 50 newtons. Okay? The interesting thing about it is if you look at it, this is node 2 here, and this is node 1. So when you look at the first element, the force acting on the spring element on the right is to the left, and that is the F2, the nodal force, on the first element. But if we look at the force at 2 acting on the second element, we get a positive number. So actually what this force is this is the force of the second element on the first element, and this is the force of the first element on the second element. So the thing about it, and I guess the point that I want to make here, is that we have a certain methodology that we employ, and if we just stick to it and be careful, it will deliver the results that make sense and that we expect. If we don't, then we're not going to get the correct results. Now I haven't. Oh, the other thing that I should mention here too. Remember that if we compare this system here with the previous system where we had a single element, so remember what we did before. The first problem that we worked, let me see if I can find it, yes, was a problem with a single element. It had the same K. Let me move this down so we can see it. It had the same K. It had the same nodal displacement to the right for both of these. This was 0.2 and 0.1 on x2. And we wound up with 100 pounds, or not pounds, sorry, newtons, as our nodal forces. So this was under compression, and we wound up with 100 here and 100 acting back that way there. But when you put these springs in series with each other, then the amount of force that it takes, so if we have springs in series with each other, let me get the example back out here. So if the springs are in series with each other, the amount of force that it takes to shorten this distance by 0.1 is half of what it takes with a single spring, and that's what you would expect. Okay, I think that covers what I wanted to cover. I think an interesting thing that you could do with this, there's several things you could do. You could try 3 elements if you wanted to, and you'll have a bigger matrix, a bigger global matrix. It'll be if you have 3 elements, you're going to have 4 nodes, so you'll have a 4x4 system instead of a 3x3 system. And you'll find that if you use the same stiffness, you'll find out that your nodal forces are less. So that'd be one thing to try, just to get some experience on your own. The other thing that you could do that we didn't do, remember with the single element, we actually worked the problem, let me find it, where we fixed the second node, the rightmost node. Yeah, we worked this problem here, where we fixed the rightmost node and we put a force on the left node. You could try this problem also with the 2 elements and see what you get, and the results should make sense. I haven't worked either one of those, but that might be something that you want to try just to gain some experience with this. Okay, and in my opinion, of course, you're gonna in the future you're gonna use if you're gonna be doing the finite element method, you're gonna be doing you're gonna be using some commercial program for doing that. But really, in my opinion, it's good to know the behind-the-scenes picture of what's going on, and the spring elements are nice because they're very simple, and you can use your intuition to see whether what the methodology is telling you makes sense. Okay, so I'll stop here. Thanks for your attention.